Hello and welcome back to Let's Code Physics, Projectile Motion Simulator. We are here to make some additions to our code today. You might recall last time we left off, we were able to launch our projectiles. In this case, we're simulating a football toward a field goal. We're able to launch those in 3D, so we've got two angles to be concerned about. We've got the proper launching angle. That's the angle that we're kicking it from the field, from the ground. But then we've got the side-to-side angle. So that's sort of, you're approaching the ball at an angle, or your foot swinging at an angle or something. It was this angle that I was never able really to control when playing sports. Actually, I was never really able to control either angle, which is why I'm a computational physicist, because here I have precise control over the angles that the football goes. And today, for the first time since we started this series, we are going to be making changes to the force that acts on this football, that acts on the projectile as it goes through the air. And I might turn off the second angle rotation because that's getting a bit cluttered there. So just as a reminder, in our code, the force on this thing is getting calculated down here, this force value. And so far, the only force we have acting on it is gravity. We've done 10 episodes now with just gravity. We've shown you all the neat things you can do with this, this basic projectile motion. Today, on the other hand, we're going to add in our first other force. And the first force that comes to mind to add is the drag force. So the drag force, as the projectile, as soon as I can get my drawer to work, there we go. As the projectile is flying through the air, the gravity on it acts consistently. It's a consistent force of mg, a magnitude of mg, and a consistent direction of downward. On the other hand, the velocity of this thing, let me draw velocity in a different color since velocity is not a force. The velocity of this thing is, I can write better than that. In fact, I can draw a better arrow than that. The velocity of this thing is changing its angle, right? So as this thing launches, it starts out with a velocity that's going like this. When it reaches the top, it has a velocity that is flat, and then it proceeds to fall down with a velocity pointing down this way. So at any point in this trajectory, it's got a velocity at a different direction and with a different magnitude. I didn't entirely keep my magnitudes consistent, but it has a different magnitude. The idea of the drag force is that it's the force of the air resisting the ball. So as the ball is traveling up and to the right in this instance, it's hitting all these air molecules along here. And I know that air is not really a compound. There's no such thing as an air molecule. The molecules that make up air, so the stuff that we have in air, they're striking against it. And that's a collision that's robbing it of some of its kinetic energy. And in particular, they're going to exert a force that on average points backwards against the velocity, and that is the drag force. So the drag force always points in the opposite direction of the velocity. Now, the drag force has a few pieces to it when you want to calculate it. For formality reasons, there's a half. Just from the derivation, there's a half left over. There's a factor of the density of the air. So the more densely packed these particles are, the heavier the drag force is going to be. So if you think in an extreme case, if you were kicking a football in a vacuum, there would be no molecules for it to hit, so there would be zero density. You would have no drag force. So on Earth, this air density near surface level is about a 1.225 kilograms per meter cubed, if I remember correctly. The next piece that comes up is the piece that we'll be playing around with today, and that's the drag coefficient. So the CD, the drag coefficient, is a pure number, and it's just a measure of how rough this surface is. It's basically a measure of the interaction between the projectile and the air molecules. So if you have a very, very smooth object, it's going to have a low drag coefficient. If you have a very, very rough object, it's going to have a very high drag coefficient. The next piece that comes up is the cross-sectional area of this thing. So this is, if you were looking at this thing head-on, you would see in this case, a circle. So for our purposes, this area is going to be pi r squared, where r is the radius of this projectile here. So we're going to pretend that our football is circular, although I guess if you look at a football head-on, it's kind of circular, sort of. I mean, basically, you just replace this with whatever value the surface area actually is. And then the most important part, well, actually, there's two more important parts, excuse me. The next part, one of the most important parts, is that the drag force goes like the speed squared. So this speed, remember, we've got our velocity being updated right here. We've got our projectile velocity being updated right here. I thought I had it set. Oh, yeah, that's right. It gets set up here for initially, and then down here it gets updated. But this velocity is a vector. And so in order for me to have a value here, I need to take this thing's magnitude and square it. And that's all well and good. That will get you the strength of the drag force, except there's a little bit of a problem in that this is a scalar, not a vector. It doesn't have the direction programmed in, and the drag force changes direction. Remember, it's always pointing opposite of the velocity. So initially, when you launch it at this angle, the drag force is going to point back this way. When the velocity is horizontal at the peak, drag force is going to point backwards to the left horizontally. And then, oddly enough, when the projectile is falling down and to the right here, the drag force is going to point up and to the left. So for half of the journey, well, not quite half, but for qualitatively half of the journey, the drag force acts in the downward direction, and for the other qualitative half, the drag force acts in the upward direction. So sometimes drag acts with gravity, and sometimes it acts against gravity. We're going to see how that plays out in our code. So I need to be able to change the direction of this thing. So for this, we're going to use something called a unit vector. We're going to multiply this thing by the negative of the direction of the velocity. So this little hat symbol here means a unit vector. The way you write a unit vector is it represents strictly the direction of a vector, not its magnitude. So the way you calculate one is you take a vector, so we take our velocity vector, there's got a harpoon, so that means it's a vector, and we divide it by the magnitude of the vector. So you take a vector, divide it by its magnitude. By default, that gives you a vector that has a magnitude of 1, so it's a direction of 1, not 1 meter per second, just 1, in a particular direction. So at each point along here, this is also the direction of v hat, v hat, v hat, can't quite fit that in, oops, v hat, there we go, for right below, I have plenty of room. And so this drag force always points in the opposite of that, negative v hat, negative v hat, negative v hat, negative v hat. And so, because the velocity is being updated, this unit vector will be updated, which works out pretty well. We can save ourselves a little bit of computational time by doing some cancellation here, but I'm going to leave it as the magnitude squared times the negative v hat, because later in another video I want to be able to modify this to incorporate a wind. So this is all assuming that there is no wind present. Oops. This is all assuming no wind present. It's a no wind scenario, if you will. So let's get started plugging this thing into our code. So for the first time in the series, we're going to add in a force, another force. We're going to take the drag force now. And so this thing, let's get its magnitude first. So we got a 1/2. We've got a air density. Actually, I guess I could just call that air density, just to be clearer. We've got the drag coefficient, and then we've got the area, and then we've got the velocity squared. So for that I need to take magnitude of projectile.velocity, and then square it. And then I need to get the direction. I need to get times negative v hat. Cool, so that's all well and good, but the but VPython is going to yell at me for not having defined all of this stuff. So let's see, these first few are all constants. So let me copy and paste those up here where we start defining the stuff about the projectile. In fact, now that I think about it, I probably need to make this projectile dot area. There we go. Projectile dot area. There we go. That way it's tied to the projectile object, just in case I ever need to change something. It's all tied to the same object. So let's see. So we start putting in the projectile information here, and I copied that little line, that little snippet of code, so that I would make sure that I had all the names the same, rather than have you watch me go on a wild goose chase to find all of the different stuff that I called these things. Let's see. Let's put this information up here. So let's go with air density. Let's make this take place in the real world, 1.225. Drag coefficient, this is the thing we'll be changing. Let's start out with a drag coefficient of 1. I didn't bother looking up what it is for a football, because we're not going to size this thing to be a football. But this we'll just take a look at different values. Actually, a drag coefficient of 1 is not terribly unreasonable. Let's see, and then I need to set the projectile area. So this thing we're modeling as a circle head-on. So this is going to be pi times projectile dot radius squared. Cool. So I've set my air density, I've set my drag coefficient, and I've got my projectile area. And my projectile is being redefined every time, so I need to redefine projectile.area down here. These I can keep up here. If I wanted to, I could loop over these. I might do that in a future installment. Let's see, let's go back down here. So I got air density, I got drag coefficient, I'm going off the screen a little bit. I've got projectile area, I've got the magnitude of the velocity squared, and now the only thing left, if I double check against my formula, the only thing left is negative v hat. And again, the way I get a unit vector is to take the vector, the projectile.velocity. Let's avoid misspelling projectile again. There we go. And I divide by this thing's magnitude. So this mag function gives me the magnitude of the vector. Just gives me the length of the vector. It's basically doing Pythagorean theorem. X component squared plus y component squared plus z component squared, all square rooted. Alright, so then that gives me my drag force. So now I've already got the negative on the v hat. Yeah, I've already got the negative there, so it'll point in the opposite direction. So don't think of this as a negative number, because remember, it's a vector. This is just indicating that it's the opposite direction of v hat. So then we're going to add to this drag underscore force. And after rewatching the animation, I think I'm going to freeze the value of angle 2. Let's change this to, so this is the approach angle. So this is the one going to the left or right. So let's just have this be a 0. Let's set the maximum to be a 0, and this way it will only loop along it'll only take that one value. I don't believe it changes angle 2 until the end of the code. Yeah, so it starts out at the minimum angle. Okay, so we should just have one loop for that. Okay, so with our drag force in place, let's see how this thing changes. It's thinking. Still thinking. Did I give it an infinite loop somewhere? No, okay, good. Okay, cool. No mistakes in my code. Awesome. And I now realize that the football code was not the best place to start this with, because most of them are making it into the field goal, and I wanted to show a complete arc. That's all right. Easy way to fix that. We'll just ignore the football problem for a second. We're going to change the launch speed. Where do we set the launch speed? All right, so the initial speed. All right, help me remember, that was 27 originally. Let's give it a much more modest speed. So we're not playing football anymore. We're just watching projectiles. Oh, that is not very much. Okay, let's make that a little bit more. Let's make that a 5. There we go. Okay, that's the projectile motion we know and love. I'm not really seeing a whole... Okay, I'm seeing a little bit of asymmetry. Maybe I need to get more angle values for angle 1. So let's go for angle 1. Where are you? There we go. I didn't call it angle 1. I called it angle. Let's take you all the way up to... let's take you all the way up to 90. And we're going to go in... Let's go in units of 5 this time. So we'll go 5, 10, 15, 20, etc. Because what I should start to see is some asymmetry in the arcs that they make, because of what we observed earlier, that that drag force is acting with gravity on one side and against gravity on the other. And one way you can see that, remember before, these used to line up, right? So, in fact, if you look over here, we do have them lining up here. So let's see, 40 and 50. Actually, that should be 45, shouldn't it? 5, 10, 15. Yeah. Okay, yeah. So you see, for example, here, you've got, let's count backwards. So we got, actually, let's count forward. So we got 0. No, sorry, that's 90. So we got 5, 10, 15, 20, 25, 30, 35, 40. What you notice here is that 40 and 45 now take you about the same distance. It used to be that 45 took you the farthest distance, and 40 and 50 matched up. But now you've got 40 and 45 kind of almost matching up. They're separated a little bit. Again, because of this drag force. Because 45 is traveling a farther distance, or is able to travel a farther distance, there's more opportunity for the drag force to take away some kinetic energy from it. So there's, let's see. So let's go 5, 10, 15, 20, 25, 30, 30. Hang on. No, wait, I'm counting the wrong side. 5, 10, 15, 20, 25, 30. 35 lines up with, I guess that's 50 there. But then they stop lining up so well, so you get this difference between them. We don't really... oh, yeah, actually, if you take a look at this one, if you look at the peak right up here, so take a look at this one. So this one is... So we go from 90 to 85 to 80. So at 80 degrees, the peak... Zoom in a little bit. The peak is right here. And so if you draw a line down the middle down here, it's not left-right symmetric anymore. Remember, one of the beautiful things about a parabolic arc is that it's symmetric across the maximum. It's a little bit sharper of a drop here than it is of a rise here. You can also see it on this one. We can see that become more pronounced if we increase the drag coefficient. Let's up the drag coefficient. Let's up it to 2 for now. And let's see what kind of a difference we get in the arc shape. This is what makes the drag force so much fun, is that, okay, yeah, I see those are definitely not lining up now. Here you're starting to see more of the asymmetry. So like if you take this this trajectory right here, if I drop down to this point, I've got 1, 2, 3, 4, 5, 6, 7, 8 units on the right, and 1, 2, 3, which one am I at? I'm at this one, yeah. Oops, excuse me. So here you've got, let's see, let's drop this one down to here. So you got about 8 on the left, but then 1, 2, 3, 4, 5, 6, 7 on the right. So there's this asymmetry to them. Let's increase the drag coefficient even more. Let's get this thing up to 5. Again, that's just a pure number, so whatever units you measure in, the drag coefficient is going to be the same. Here you can definitely see the asymmetry. So take this peak right here. It's peaking at about 1 here. Let's see, and where are you going to? You're going to about here. So to the right, it goes 1, 2, 3, 4. I know you can't see my finger pointing at the screen. 1, 2, 3, 4, 5, 6. So there's a difference of 2 units in terms of the trajectory before the peak and the trajectory after the peak, which is kind of cool. Let's see. Let's put this thing up even further. So let's say this is a very, very rough object. Here, even in these first few, you can see this difference that it makes. In fact, some of these, you see that the peak recedes much more quickly with the angle. So this is some of the fun stuff you get with the drag force. You get that there's this break in the symmetry across 45 degrees, and you get that there's this break in the symmetry across the maximum. All right, now let's go back to the football case, because I want to try something here. Let's see, where was that initial speed? Let's back up this way. Let's put that back to 27. So let's say we're back to footballing. And let's change this back down. I think we had a maximum of 40 before. Let's go ahead and make this one up to 45. With a drag coefficient of 10, let's see how many can make it to the field goal. Yeah, so you see with this one, with this much drag, that speed of 27 is not doing very well. It's not making it to the field goal. Let's see. So that was with our drag coefficient of 10. We previously had no drag coefficient. They were all making it in. So let's see if we can get one where half of them make it in and half of them don't. Okay, so here we get some of them to make it. Oh, that last one, is that one gonna make it? Okay, that one made it. That one makes it. Oh, we actually stopped a little too soon there at 45. So here, remember previously these were making it in and these were not. So this is a little bit more realistic. In fact, let me take just a break. Let me look up, see if I can find the drag coefficient of a football. Alright, so according to this paper that I just found, the drag coefficient of football is around 0.05 to 0.06, depending on whether it's spinning or not spinning. And so, yeah, so when the thing spins, that's going to affect the drag coefficient, but also it's going to change, if it's tumbling, then that's going to change the surface area. Let me just double check what their drag coefficient is. Just to make sure that we are using the same, their definition of the drag force, just to make sure that we're using the same, values here. So their drag coefficient is drag force divided by 1/2 v squared a, which is a function of the Reynolds number VDL, where v is the wind velocity, something is the air density, A is the normal flow, D is the diameter of the football, and is the kinematic viscosity of the air. So I think they have a few, it looks like they have some variables missing in their sentences here. But yeah, that's not going to produce a dimensionless number because it doesn't have the, oh, you know what I'm guessing? There seems to be a blank there. I'm guessing the air density is supposed to go there because here they've got a blank is the air density. Okay, so I think they are using the same definition that I am. So thank you to Watts and Moore. If y'all wouldn't mind maybe making a little edit there to put in the character that's missing. So let's put this down to a more reasonable size of about, let's go with the lower value, 0.05. Actually, let's go with the average, 0.055. And let's just see what that does to our average kicker here. Okay, so for our average kicker, it doesn't make that huge of a difference because when we go with a drag coefficient of 0, it's, the same ones are making it in as made it before. So that's good. Let's put this back up to 0.055. In fact, let's even say you've got a particularly bad football. Let's put this up to 0.1 because I want to end with just one thing. I took out the angle launch. I took out the angle loop for here it is. It was right above me. I took out the angle loop here. I want to put this back in now and just see what the drag force looks like in 3D. And in fact, let's even up this a little bit. There we go. So I'll leave you now with our loop over the second angle as well, getting a look at at what our drag does to our kicking here. So we're still making it in, but you can see the again the asymmetry in the kick there. I'd also expect there to be a little bit of a difference as we go along the angle in the lateral direction. Yeah, I suppose there's a slight difference. I'd have to look at that in more detail. But anyway, we have added in our drag force. So what we are going to do next time is start adding in a crosswind to this thing. So this was assuming that there was no wind present. Next time we're going to add in some wind. So that'll be a lot of fun. So thank you so much for watching. I will see you next time. Bye-bye.